Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 45. So in the last class, we were looking at the transition moment integral, and I was describing to you the various terms. And I was telling you that the wave function term over there, right? The wave function term there could be associated with quantum mechanics. How it could be associated, I did not tell you. Basically, by doing a lot of math, we can associate the quantum numbers with the wave functions, right? And there is also one more wave quantum number called as the spin quantum number, which can also be associated with the overall molecule. Okay, right? Now, the evaluation of this integral leads to what are called as selection rules. Okay, I have not told you what the selection rules are going to be and what form they're going to be taking. What are the selection rules for? How will they be connected with the intensities? I have not told you yet. Okay, and likewise, I also just told you that the selection rules will be expressed in terms of the quantum numbers. How this is done and how the math is done, which lead to the selection rules to be expressed in terms of quantum numbers, I've not told you, and I'm not even going to tell you in this lecture at all. But the final results, right? The final results we shall be seeing in a few lectures on. I will now just briefly explain the connection between selection rules and intensities of lines. Okay, so first up, selection rules. So typically, if you recall, in an earlier tutorial, while we were discussing the connection of dipole moment, right? Dipole moment in obtaining purely rotational spectrum and in obtaining the vibrational spectra, we said that the molecule needs to be possessing a permanent dipole moment, right? For it to be exhibiting a purely rotational spectrum. Likewise, there must be a dipole moment change, right? For a molecule to be showing vibrational spectrum. We looked into that, remember, from a tutorial, right? Now, these are examples of selection rules. That is, what are the processes, okay, right? Selection rules typically tell us what kind of transitions, right, are allowed. When we say allowed, right, we mean that the intensity is going to be large. Okay, right? Versus what kind of, by transitions, what I'm talking about? I'm basically talking about an electron going from, state 1, from initial to final. That is what I'm talking about as a transition. The initial state can be a lower energy state or it can be an upper energy state. Okay, just that the final state is decided accordingly, because we don't know what type of spectrum we are particularly talking about. Are we talking about an absorption spectrum or are we talking about an emission spectrum? Okay, those details, I shall be explaining to you when we go to the specifics of the absorption and emission spectra, the infrared spectra, and the microwave spectra, etc., etc. Okay, so right now, by a transition, please note that I'm referring to a state where I go from an initial to a final state. Okay, all right. So the selection rule tells us that what kind of transitions are allowed. By allowed, I mean the intensity is going to be large, versus what kind of transitions are forbidden. So see, the word forbidden in English means that it is perhaps not going to happen, okay? But in the context of spectroscopy, forbidden merely means that the intensity is going to be very feeble. So I'm merely qualifying it now, right? I've not given you any units or any numbers, okay, right? Some of the numbers will come later on. But for now, please note that by forbidden, I'm not saying that something will never happen. By forbidden, it just means that the intensity will be very feeble. Okay, right? Now, this is what the selection rules are going to tell us. Now, I will now delete this page and the selection rules, okay, right? An example of a selection rule would be that, for example, one, in vibrational spectra of molecule, that is, it happens in the infrared range. Remember, I told you in the tutorial, okay, right? Typically happens in the IR region, right? Only those transitions which are associated with a change of dipole moment, right? Are allowed. Okay, so please note this. So in any vibrational spectra, right, only those transitions will be allowed when a change of dipole moment is possible for the molecule. Okay, right? Are we good? So this is an example of a selection rule. Okay, now notice that the same thing, right? This is what is example of a gross selection rule. What do I mean by gross? By gross, I refer to the idea that this is a general idea, right? But specifically for rotational transitions, specifically for vibrational transitions, and specifically for electronic transitions, there are going to be particular, more pointed selection rules, right? Which can be derived from that integral we discussed in the last class, which will be expressed in terms of the quantum numbers. All right. So the reason why, I'm spending this time, right? I'm spending this time with these qualitative ideas of like selection rule and the gross selection rule is to explain to you clearly that even by making qualitative ideas, right, we can get an idea about the intensities of transitions. Okay, right? For example, if like during the transition there is going to be no change in the dipole, no change in the dipole moment of a molecule, right? Then the transition is not even going to be allowed. All right? Are we clear? I have, of course, not given examples. And with this, I shall be stopping my discussion on selection rules themselves. Okay, with the caveat that note more on selection rules to follow when we specifically discuss rotational spectroscopy, vibrational spectroscopy, and atomic spectroscopy in the context of the interstellar medium and detecting molecules in space. Okay, right? For now, please understand that selection rules tell us what kind of transitions are allowed, right? And we can have gross selection rules, which are statements of the form that, oh, there needs to be a change in the dipole moment, etc., etc. Or there could also be specific selection rules about which we have not seen yet in this course, which involve quantum numbers. Okay, that part will be 100% clear to you when I discuss, like Bowen selection rules. All right, yeah. Now see, we already see, two types of transitions, right? The allowed transitions and forbidden transitions, right? Elaborate about them a bit now. A little bit about allowed versus forbidden transitions. See, when some transition is typically allowed, right, based on a selection rule, in other words, when the magnitude of the transition moment, right, is going to be large, we say that the transition happens very fast. So allowed transitions happen very fast. By fast, okay, right, I'm referring to a time scale, right, on Earth, right, of the order of picoseconds. Okay, right? Now, forbidden transitions, right, they happen very slowly. Okay. Now, the allowed transitions are fast, right, of the order of picoseconds. That you can imagine, right? I mean, the energy gap, especially the rotational energy gap between any two states, is not so high. This indication we got from the ammonia inversion problem, right? We saw that based on the energy gap between the first rotational excited state and the ground rotational excited state, the temperature of the gas sample was obtained to be what? From a previous lecture, what was the value? It was around 3 Kelvin, right? So, the energy gap isn't that high, okay, right? So therefore, a lot of allowed transitions happen very fast between these two energy states, which are very closely lying, okay, right? But there are also going to be very forbidden transitions, right, which are forbidden in the sense that they take a lot of time. Now, in the context of astrochemistry, okay, in the context of astrochemistry, please note that forbidden transitions are extremely important too. Why is that? Well, let's say, for example, right? For example, instead of a transition happening in the time scale of picoseconds, let's say that it takes approximately, I don't know, 15 million years. Okay, right? For some transition to take place. We're talking about like what? A million is like 10 lakhs, right? In our Indian unit system. So this is going to be 15 into 10 lakh years. Okay, right? That is 150 lakhs years, right? Yeah. So even if a transition, takes place in such a long time scale, right? Even that will happen, right? Will happen in the interstellar medium, right? Because the Earth, the age of the universe is much larger than this, right? Because the universe is much, I would say, like much older, okay, right? Of the order of billions of years. Recall our very first few lectures wherein we were discussing about Big Bang nucleosynthesis, etc., etc. Okay, so therefore, right, the forbidden transitions are also very important in astrochemistry. Okay, right, and even though the forbidden transitions happen very slowly, for astrochemical reactions to detect molecules in space, they are very, very important too. All right. Okay. So I want to briefly give a summary of what all we have seen in the last two lectures, because we've been like meandering along quite a few details. Okay. We initially like we're looking at the transition moment integral. Okay, right? I'll also just sum it up here. So we started off with the UFI, right? And I was explaining the LHS and RHS terms, right? And from this, we were led to the idea of selection rules, right? And from the selection rules, we were discussing about allowed and forbidden transitions. So this summary is just to tell you not to get lost. And we also told you that the forbidden transitions are important in astrochemistry, especially important in all right. So we are clear about where we are, right? Notice that the idea behind this MUFI was also to connect with intensity of a spectral line. Okay, right? So the idea of this was to connect with the intensity of a spectral line also. Now, finally, right, we are going to be looking at a formula, right, for the intensity of any spectral line obtained. Okay, that I'll write in page 8. So this contained in page 7 is just summary of last 2 lectures. And of course, don't forget that as part of, like explaining LHS and RHS, I was also clearly telling you the significance of associating quantum numbers with any wave functions. That was very important to understand selection rules, about which there is a lot more to see, right, in this course. Okay. So this is now going to be page number 8, and I told you that I'm going to be giving you a formula for the intensity of a spectral line. Okay, right? So the intensity I, right, of any spectral line can be obtained from the following formula: n times g1 by g2, right, times e to the power minus delta E by kb times T times the magnitude of mu Fi. Okay, right? So now you see the connection, right, between intensity and this transition moment integral as well. Very important. Okay, right? Now notice this point. What are the terms here? I is of course the intensity. Let me just call this, equation. I think we already called the other equation is I. So let me call this equation. Okay, let's not call this equation anything for now. Okay, right? Let's just look at this equation in page 8. We'll call it equation 8. Okay, right? So if you consider this equation 8 here, right? Now the left hand side is the intensity. On the right hand side, this, we've been discussing it for close to 1.5 classes now, this mu Fi. Kb is Boltzmann constant, T is the temperature. What is delta E? Delta E is defined as E2 minus E1. Okay, right? So that is E to the power. So we kind of have an idea. When is this valid? Well, this is valid under local thermal equilibrium conditions, right? Because we saw this expression in the context of the local thermal equilibrium, remember? So this G1 and G2 are the degeneracies. We explained what degeneracies were a few lectures earlier, right? And the only term which we didn't discuss so far is N. N is the total number of molecules involved, which is of course going to be a large number, okay, right? Which is going to be a large number. So this is the expression obtained for intensity. This is the formula for intensity. And note again, did not derive, okay. I just gave it to you. I gave it to you, right? I did not derive this. I gave it to you. And this equation, that is equation 8, connects your intensity of the spectral line with the transition dipole moment, okay, with the transition dipole moment integral. All right. Now see, this is a very important equation for many reasons. I will explain all of them now. So I'll delete this part. See, okay, the point I want to tell you is that, see, in equation 8, okay, right? Now, this term right here, this mod mu Fi, you can calculate from quantum mechanics. Okay, that's done. The Boltzmann constant, you know it's a constant. The temperature, right? The temperature you can either get, okay, right? You can get from other ways, okay. By other ways you can get the delta E term. When I say by other ways for temperature, it is not just from this equation, okay. There are other ways you can measure the temperature of, let's say, like any sample on space, okay. So this also you can get by experiments. This delta E also you can measure by experiment, okay, right? So delta E also you can measure by spectroscopic experiments. G1 and G2 you get to know by quantum mechanics, okay, right? So from quantum mechanics you get to know G1 and G2. And I is also something you can experimentally measure, right? Of course, this is a formula to calculate I, but I is also something you can experimentally measure. So using all this, right? Using all this, what this equation tells you is that equation 8 tells you that if I were to be obtained experimentally, if I were to be obtained via experiments, you could calculate n, which is the total number of molecules. Now, this is a very, very, very important point. Okay, right? Why is it an important point? Hey, we can now not just detect molecules in space, but we can also detect how many molecules are in space. Recall, in the earlier lectures, I was giving you the various number density values. It is by using some such equation. Okay, I'm not saying exactly because the numbers we obtained were number densities. Here, this is just like a number. Okay, how to connect the number with the number densities? We'll soon see. Like once we study a module on telescopy and radio astronomy, etc. Okay, right? For now, for the first ever time in this course, I've told you that we cannot just qualitatively detect molecules in space, but we can also quantitatively detect them, right? So we can find out how many molecules are there in space by using this equation. And don't forget, whenever we use an expression of this type, right, we always assume what? We always assume that the system is in local thermal equilibrium, that is LTE, right? Are we good, right? So it is under LTE conditions. It is under LTE conditions that this equation is valid. I did not derive it. I need not derive it. Okay, right? Because that is way beyond the scope of this particular course. But by using it, right? I can calculate the number of molecules if I measure I experimentally. But let's say that I don't. But let's say that I have a. This is on space, right? This is on space. On Earth, if I can calculate this number of molecules, because I know the sample I take, right? On Earth, I know this. I know how much sample I take, so I can calculate the number of molecules. So based on that, I can predict, like the intensity of an experimental spectral line. Are we good? Right? This equation, that is equation 8, is used in multiple ways in space, right? You get I from experiment, right? You get I from experiment and can predict or like get N from equation 8. But on Earth, right, when you actually record the spectrum of a sample, on Earth, right, you can actually, N. N is known, so you can predict the intensity of any signal, right? Based on this equation. All right. And of course, when I say in space, okay, right, what I mean is you get I from experiment. That is, what does the experiment perform? We're talking about, attaching a telescope with plus some kind of a spectrum recording device, okay, right? I'm just calling it a spectroscope, etc. Okay. Of course, you're not going to go to space itself to perform the experiment. You're performing the experiment always from Earth, right? Or maybe, like if you have space stations, right? You could perform the experiments, slightly afar from Earth. But in any case, you get information from ISM and all those regions, right? You use a mixture of telescope and spectroscope, etc., and you get the light that is emitted by a distant interstellar object, right? So from that you get I. Okay, so from that you get I and use that I to get N. So therefore you can calculate the number of molecules present in space, which is very interesting, right? So that is the modus operandi on space. On Earth itself, right, how much sample you take, right? So therefore you can predict the intensity and you can cross check, okay, right? You can cross check with experiments. You can cross check with experiments, right, that the intensity obtained is indeed matching with this, okay, right? So overall, this is a very powerful equation. And don't forget, yet again, Under what condition is this equation valid? This equation is valid under conditions of local thermal equilibrium. What do I mean by local thermal equilibrium? Well, currently all that I'm talking about is that, whenever I can get what is called as a Boltzmann distribution, then local thermal equilibrium is valid. In fact, in a tutorial, okay, right, I shall be explaining a little bit more about local thermal equilibrium. All right, yeah. Now, so what did we do? So we were talking about selection rules, right? And after that, I gave you an expression for intensity based on local thermal equilibrium and said that this is a powerful equation using which, right, we can both get the number of molecules, obtained in space that led to this particular spectral line, right? And not just that, we can also predict the intensity on Earth itself if the number of molecules is already known, right? Noting that all these terms, right, all these terms could be calculated. Note a caveat though, this term T alone here, right? This term T alone should be measured from some other way. Okay, that's the important idea. So this term T has to be measured from some other way. Okay, you cannot have two variables in one equation, right? So that's it. All right. Now, before we proceed further, I'll just, complete the whole picture. What I'll do is, I will now give you, so this will be the concluding part for this lecture. Now see, using some quantum mechanics, the good news is, we're not going to discuss it in this class. Not discussed in this class. It can be shown that, okay, right? Right? Your Einstein, recall we were discussing about the Einstein coefficients, right? Your Einstein coefficient B12, I believe, okay, right? The one that is talking about absorption, okay? The Einstein coefficient can also be connected with this transition moment, okay, right? As the square of the magnitude of the transition moment by 6 epsilon naught h, where epsilon naught is what? From your 11th standard physics, you've been seeing this term epsilon naught. What do you think it is? It is the relative permittivity of vacuum. Okay, I mean, I'll give it to you as a homework to get its units, all right? So what did we do? So through B and mu fi are connected. So once we know B12, I can get B212. And once I get B21, I can get A12. Because we already derived the connection between these three expressions. And what are all these related to? All these are related to the rate of transition. The rate of electronic transition from a lower level to a higher level, correct? Right? So now all these coefficients are connected with this term, and this term is in turn connected with the intensity, right? So the rates of transition are overall therefore connected with the intensity, right? And all of this is going to be extremely useful to detect molecules in space, all right? So are we clear? We had a lot of meandering details. We had to discuss a lot of details along the way, but we have come back and connected, what we said we would connect in the first place. That is to connect the Einstein coefficients with the intensities. Noting that a lot of the mathematics, in fact, all of the mathematics involving quantum mechanics, we have not even touched upon in this course because it's the first course in astrochemistry. All right. So on that note, I'll end this lecture. And in the next lecture, we shall be looking at some more features of the intensities of spectral lines and how will the spectral lines look like actually, all right, which are useful in detecting molecules in space. All right, thank you so much. Have a good day.